The lore of Greek mythology has it that in the 5th century BC, the Greek mathematician Hippasus made an incredible and blasphemous discovery. This was when he realized that the length of the diagonal of a unit square, a number equal to the square root of 2, was not a rational number. That is, a number which could be expressed as the ratio of two whole numbers, but rather an irrational number. In response to this astounding discovery, his peers in the Pythagorean school very kindly responded by one day throwing him overboard on a sea voyage and letting him drown. Now, the Pythagoreans believed that numbers were the spiritual essence of reality, that the universe emerged from the cosmic interplay of harmonious proportions. And the idea that there existed a number which could not be expressed harmoniously, which could not be expressed in beautiful proportionality, was so appalling to them, so against their ideology, that it merited murder. Now, of course, this story is entirely apocryphal. There's no evidence whatsoever that suggests the Greek mathematician Hippasus was murdered in such a fashion. Additionally, the idea that the Pythagoreans worshipped numbers is only loosely supported by historical texts and sources. However, there's a kernel of truth in every work of fiction, and this story, if not necessarily true, is certainly very believable. That is, it's plausible that something like that could have actually occurred. And it's plausible because of the nature of mathematicians. Mathematicians are a very self-venerating group. They carry this sort of aura, this oracular aura about themselves in their work. Their craft penetrates the mysteries of the beyond. It transcends the immanent. It reaches into the mind of God to, lay bare the structures of reality. And that is the view they often carry. It's very profoundly spiritual. Mathematicians have a profoundly spiritual sense of their work and their craft. And that sense can often give way to a certain fanaticism, which is why the story of Pythagoreans murdering Hippasus is not altogether so unbelievable. Moreover, the idea that all reality is somehow mathematics in its purest essence is not an ancient view. It's in fact the view that is prevalent today, the view that modern science and modern physics takes. And if it's not readily apparent that this is the case, well, that is the point of today's discussion. Welcome to the Dialectical. Today, we want to know, is all of reality just math? And if not, why does math seem to play such an intricate role in all of rational progress and rational discovery? And what is the meaning of the unreasonable effectiveness of mathematics in the natural sciences? And lastly, can we redeem poor Hippasus and his discovery of irrational numbers? And is the harmoniousness, the beauty of mathematics subjective, or is there something further to it? We're going to discuss all this and more, starting now. Alright, so this is the 4th episode of the Dialectical, and to recap the episode from last week, we talked about how physics in the 19th century went from being a very empirical and physically based science and moved into the territory of a much more abstract and what's called Platonic ideology. So essentially, the central point of the episode was that in the 19th century, you had all these mysterious phenomena in electromagnetism which appeared in the course of the study of electromagnetism, which no one had really good explanations for and which were very confounding. So we weren't able to explain them, but we were able to mathematically describe them and mathematically correlate these phenomena. And so the prevailing philosophy of the time, the prevailing ideology that emerged was one of positivism, which was the philosophy that you shouldn't ever say more than you know, you shouldn't speculate or infer more deeply as to what's going on. You should only just stick to observations and just stick to facts and just stick to correlations. In this last episode, we discussed a lot of problems with the positivist view, which is primarily that it's anti-science. It doesn't allow you to make deeper inferences, make deeper conjectures, or build models that lead to deeper knowledge and better future models and better future predictions. So in the absence of any real explanation for these phenomena that we all saw, that physicists all saw in the 19th century, the positivist view left this vacuous hole in the heart of physics, which was what explains all these observed phenomena. And what ended up filling that hole was mathematics. That was the ideology that got adopted. This was called Platonism, the idea that reality is just mathematical forms. So how is this evinced today? Well, our two major modern theories are general relativity and quantum mechanics. And the idea of general relativity is that the theory explains reality as being space-time geometry. Reality is nothing more than a manifestation of this complex, abstract mathematical construct. And then in quantum mechanics, you have all sorts of bizarre mathematical constructs, and you can't say what's exactly real or not, but you just have all sorts of very, very abstract structures. So both of these major theories are rooted or are explained by math. They both take the route that all these phenomena we observe have no deeper meaning other than they are the expression of the mathematics itself. So this is Platonism. This is the prevailing philosophy and ideology of our age. But what's so insidious about modern times is that people will pretend that this is not the case. You'll often hear, the saying, we don't do philosophy anymore. Science doesn't need philosophy, which is, one, an outright lie, but two, it's an attempt to basically disguise the fact that we are employing this philosophy, this ideology. It is an expression of fanaticism, of mathematical fanaticism, because it is the mathematical fanatic trying to hide the fact that he is doing something which is ideological, purely spiritual and ideological in nature. And the whole idea that science is separate from philosophy is intrinsically absurd. You can't not have a philosophy when doing anything. So you do anything at all, you have to have a philosophy of what you're doing, right? You go to the gym, you have a philosophy of fitness. You're a doctor, you have a philosophy of health. You do science, you have a philosophy of science and how science should be done. And that current philosophy is Platonism, is the idea that the math should explain everything and that we should look for beautiful math. And a really great way to see this is to kind of examine the trends of like, if you read physics journals and papers where people are putting forth kind of like more grand unification theories and things like that, the way they couch their language is very often very funny. So if you put forth a paper that says, hey, I want to explain gravity as a phenomena in a wave medium where it's like secondary or tertiary phenomena of how waves work, well, you'll get rejected from all the journals. You'll get laughed out of the room. The modern physicists, they're gonna throw you overboard and drown you. But if you instead put forth a paper where you say something like, well, reality can be modeled as a transfinite, recursively self-similar topological space whose metric tensor exhibits gauge invariant holonomy and matter arises as eigenmodes of the Laplacian acting on non-abelian fiber bundles, or something like that, that paper will get accepted, and it's completely acceptable language, even though it makes absolutely zero sense. You're basically just saying reality is just this new mathematical structure that I just came up with, and it sounds sexy, so let's go with it. And that's the fashionable thing that happens today. So basically, any new theory of reality has to be a theory that explains reality via math, because that is the reigning ideology of our era, that math explains reality, that reality is just math. So let's take a look at this view then. Is reality just math? Is it an unreasonable view or a reasonable view to have? And if we take that view, what problems might arise from it? All right, so let's talk about the first problem we see with this ideology or this philosophy. That problem would be the gulf between empiricism and mathematics. So if you want to say reality is mathematical, right? But when you do science, you also try to stay empirical and stick to what is observed. So the biggest problem we see in our end with the assertion that math is reality is, well, where do you observe math? When is math observed? Say, for instance, the number 5. Have you ever observed the number 5? We ask you to, if you believe you have, to go out now and go fetch the number 5. Go bring it, and come show us that you have the number 5. And you think, okay, well, that's easy, right? And you bring back 5 apples, and you be like, okay, here's 5 apples. There's the number 5. But that's not the number 5. That's 5 apples. You don't ever see numbers in nature, right? A number doesn't exist anywhere in nature, right? You can't ever find the number 5. You're always going to have 5 of something. You're going to have numbers which are attached to these physical real-world objects. So in that sense, there is no reality. There's no empirical reality to math. It is a component of describing that reality. And in this way, this really resolves a lot of the fundamental, issues that people have with mathematics. So, we had the Pythagoreans who were completely freaked out by irrational numbers, like, oh my God, irrational numbers can't exist. And then later on, in Europe, you had people freaked out about complex numbers or imaginary numbers, and you still have people freaked out about imaginary numbers today. Oh my God, how can imaginary numbers exist in our mathematics, right? But all numbers are imaginary. There's no such thing as a real number that exists in nature. So, like you say, the number I, the imaginary number, if it freaks you out, why? Why does it freak you out? Like, go find I out there in nature. You're not going to find the number I, right? You're only going to find equations with I in it, which describe certain physical systems in the real world, but you're never going to be able to isolate that I. Similarly, with this is an argument that might have helped Hippasus save his own life. It might have kept him from being thrown overboard. Hey, Pythagoreans, Hippasus might have said, I didn't actually ever show that irrational numbers exist. All I actually showed was that the length of the diagonal of a unit square, that the ratio of this length to the length of the square sides cannot be expressed as a ratio of whole numbers. That's all that's been shown. He didn't show that irrational numbers actually physically exist. All he showed is that we need them when we describe things that do physically exist. So all math is coupled to something, right? So you have your 5 of apples, you have your 10 vehicles, you have your 100 raindrops or whatever. And the laws of physics are no different, right? F equals ma. Those aren't just pure numbers. Those numbers are attached to physical objects or physical constructs that we believe exist independently of our perception and of our consciousness, that we believe really exist in reality. So to us, that's the biggest issue with this philosophy, this Platonic philosophy. Now, you can sort of get around it by being like, say those 5 apples, right? Well, maybe the apples themselves are defined by further mathematical structures. And so you can kind of poke it in that direction and say, well, maybe the physical objects that we attach our numbers to and our mathematical physical laws to are themselves just deeper, more complex structures of math. And this is, of course, where you really get into the heart of Platonism. For instance, in his treatise Timaeus, Plato would have said that, yes, the apples are just the interplay, the combination of the 5 regular solids acting out some sort of cosmic harmony. But it's a struggle. It's a struggle because to connect it back to empirical observations, to connect it back to real world things, everything in math is usually describing something. It needs an object. And if you want to say that all reality is just the 5 regular solids, well, you're never going to directly observe any of those regular solids. So when you do say something like that, you're definitely crossing from the line from empiricism to some sort of philosophy or belief or ideology. And that's fine. You need philosophy. Again, you need philosophy to do science. So you're going to have to make an inference at some point. And the Platonists would say the inference you want to make, perhaps, is that those physical things to which our mathematical laws are attached are just more mathematical structures. And of course, when you do that, then you start to wade into the problem of like, well, how can there be irrational numbers? How can there be complex numbers. What happens when we discover math that we don't feel is harmonious or beautiful? Like, then that's when the fanaticism begins, and that's when the hippices start getting thrown overboard. So it leads to problematic circle. It's appealing, and it's easy to understand the appeal, but it doesn't seem super viable. Okay, but maybe you're like, well, what about the why of math, and why is it so good and so effective at describing reality if it is not somehow part of reality? And this was the argument essentially put forth in a famous essay by Eugene Wigner published in 1960 called The Unreasonable Effectiveness of Mathematics in the Natural Sciences. So in this essay of his, he basically puts forth, the thesis that we had these mathematical structures that were developed and that they suddenly one day became almost miraculously useful and effective at describing certain aspects and systems in physics. Particularly, he pointed out several examples in quantum physics. And to him, the fact that this worked out this way was very inexplicable, and offered proof that math is a fundamental part of reality, if not reality itself. Now, having heard of this paper for a long time, we were excited to actually finally sit down and read it, and it turned out to be a little underwhelming. Its argument is not very strong at all. In fact, it makes almost a stronger argument for its opposite case, when it kind of talks about how the basics of mathematics and the foundational layers of mathematics, Euclidean geometry and algebra and all that stuff, really emerged out of the necessity of trying to describe the world around us, and in that sense was almost empirical. But the bigger problem with this paper is that it makes a logical fallacy that we actually discussed in the last episode. So it's the fallacy of confounding the unusual with the abstruse. Basically, it's the fallacy where you see something that you don't understand and you think, how can this possibly be explained? And you can't see an explanation. And because you can't see an explanation, you therefore assume that there isn't an explanation. And that's basically what Wigner does in this paper, where he basically says, wow, we developed these mathematics like, say, differential geometry, and then one day it just miraculously seemed to apply to our physical theories of reality. And my gosh, how could that be explained? It couldn't be explained. There's no explanation, therefore math is reality. And that's the basic gist and basic argument of the paper. But there's a lot of problems with this argument, and we're going to try to enumerate them as clearly as possible. The first one is the one that Wigner himself brings up, which is, most mathematics was developed around describing actual reality and had actual practical immediate purpose. In that sense, the effectiveness of mathematics isn't at all unreasonable. It is perfectly reasonable. Basically, why does mathematics describe reality so well? Because that's what it's made for. That's why it's like there in the first place. Basically, you're asking a question which is like asking, hey, why is language so great for communication? Well, that's what language evolved for. That's why it's there. That's its purpose. If it wasn't good for communication, we wouldn't be using it. And if math wasn't good for describing reality, we wouldn't be using it. Now, what about the cases where we invented some abstract mathematics and then later it turned out to apply to something? Well, again, you can't just assume because you can't immediately come up with an explanation that there isn't one. If you want to approach it scientifically, you have to assume, there is an explanation for it. You have to assume that if you're doing science, and you have to keep looking for that explanation. So it's not at all scientific to just give up and be like, well, it must be magic, right? But the real and biggest problem with Wigner's argument is that most mathematics isn't effective. Like, for every mathematical structure that ends up having an application, a really useful, precise, great, wonderful application, there's dozens, hundreds, not way more mathematical structures that are absolutely useless and have no purpose whatsoever. And you've never heard of those because they don't have a purpose. For instance, I personally remember growing up, thinking it was really weird. Like, so you had addition, right? And multiplication was repeated addition. Then you had exponentiation, which was repeated multiplication. And then it just stops. And I always wonder, like, why does nobody talk about the next step? Like, you've repeated multiplication to get exponentiation. Why not repeat exponentiation? And like, it seemed very natural, the natural progress of mathematical structure to continue. And so, it turns out there is a mathematical structure which does that. It's called tetration, or some sort of higher power operation or something. But the reason you've never heard of it, the reason it's not taught, the reason it just stops there is because there's no real world application really for it. And so there's all sorts of mathematical structures like that, which are just completely ineffective. And so, math is it's very imaginative. There's all sorts of ways, possibly infinite ways that you can take it. And essentially you're picking out of that infinite class of possible structures. You're picking out a very narrow range of structures and then being like, oh my gosh, those structures work so well. Reality must be math. It's not very logical. So it's not a correct statement to say that math is unreasonably effective. Where math is effective, it's reasonably effective because it's been developed to be effective. And where math is not effective, it's reasonably ineffective because it just doesn't have any application, and it was just invented on whims and seeking out, new structures and new ideas. Okay, but this still leaves the possibility that, reality is a specific mathematical structure, and, we're weeding through all the non-applicable mathematical structures and trying to get to the heart, the essential ones that are reality in some way. So, we don't need the unreasonable effectiveness of mathematics to posit Platonism. We can still understand that math works for a purpose, but still believe that there's a specific mathematical structure that causes, explains, or is reality. And so this brings us to our final viewpoint of the day, which is probably the most important one and the one that's impacted us the most in our pursuit of further and deeper knowledge in the physical sciences. And this problem, this really big problem for the Platonic view, there is not a single theory in physics which can be described by a unique mathematical structure. So if you want to posit that reality is mathematics, for instance, if you want to posit that gravity is just space-time curvature, then you have to show that mathematical structure is the only one which gets the predictions, which explains or accounts for the correlations, which does all the right, mathematical stuff and gets you the right answers. But this is not the case for any of our modern theories. Every theory has multiple mathematical structures that will give you the same predictions, the same results, will account for the same empirical observations. Now, this fact is not very well known at all, especially not in popular culture or popular media. And most people intrinsically believe that, these mathematical structures are reality because they believe it's the only mathematical structure that's possible to account for the phenomena. But it's just that's not the case. It's not true. So, for instance, where we see this in all our theories: special relativity, general relativity, and quantum mechanics. We'll tackle briefly right now special relativity and general relativity because we have a better grasp and foundation on those, but is also very much the case with quantum mechanics as well. So special relativity, right? A lot of the understanding of the empirical basis of special relativity is rooted in the belief that the math of special relativity is the only math which gets you the right answers, right? So physicists believe that this Lorentzian geometry is the only mathematical construct which can account for the empirical phenomena. But this is not true. As we talked about, a number of videos, the Lorentzian geometry is basically a convention choice. It's based on how you choose to synchronize clocks in your frame of reference. So if you always synchronize clocks in your frame of reference, assuming that light is traveling isotropically in your frame, then if each and every observer in each and every inertial frame does that, they all assume that light always travels isotropically in their own frames, then you will recover this Lorentzian geometry. But you can have observers do different clock synchronizations. Different observers can synchronize their clocks differently in different frames, or they can all synchronize their clocks the same way in different frames, but they can do it by assuming anisotropic light instead of isotropic light. And basically this leads to a whole class of geometries, all of which faithfully predict all the empirical phenomena. So you have the Lorentzian geometry, which is the geometry of observers assuming isotropic light in their frames, but you could also have sort of would be termed Reichenbachian, yeah, something like that, geometries where, you have non-invariant light, but you still have these geometrical relations and these geometrical structures which account for the phenomena. And they're all equivalent. These are equivalent classes of descriptions. They are different mathematical structures which all describe the same physical system. Now, we see this in general relativity too. Most people believe general relativity is empirically verified because they think that the space-time manifold construct, mathematical construct, is the only one which describes reality. But this is not the case. So in addition to space-time, you can describe gravity with space-time curvature, but you can also describe gravity with something called torsion fields. This is called teleparallel equivalent general relativity. And in this setup of general relativity, there is no curved space or time. It's all flat space-time. And instead of having, curvature at certain points on the manifold, which describes gravity, describes the strength of gravity, you just have instead on this flat space-time background, you just have these torsion fields, which are essentially tensors, which contain information about how gravity is altering or affecting frames of reference. Again, it's a completely different mathematical structure, but it describes the same physical system just as well as space-time curvature does. Now, with general relativity, there's also lots of suggestion that there's other mathematical structures which also describe it. So, as we've explored, very simple, very basic setups where you have like one-body static one-body systems can all be described using Newtonian physics and Newtonian classical space and time framework physics. So you don't even need, higher, more advanced geometries to describe the phenomena. You can account for them in other ways, with other mathematics. And again, you'll see something similar with quantum physics, but we're not going to get into that right now. So this leaves a gaping hole in the Platonist philosophy. If you want to say reality is just math, well, you have to have a unique mathematical structure. But so far, we've never had a theory of physics which can't be described by multiple mathematical structures. So how is reality this specific structure when you can also have this structure which produces the exact same reality? It doesn't cohere. It's not a logical explanation for what is the essence of things. So you're going to end up having to subjectively assign why some mathematical construct is better than some other mathematical construct. And this is where a lot of people make appeals to beauty, mathematical beauty. You'll hear so much people going on and on and on about, general relativity, it's such a beautiful theory. The idea that we just follow geodesics on a manifold is so beautiful. But what is beautiful about it? What is beautiful about a geodesic? It's cool. And like when you didn't understand it before and then you do understand, you're like, oh, that's cool. That's really neat. Like, yeah, you feel a high from having understood something and having grasped a new concept. But what qualifies that to be a better theory? Like, it's not any simpler than, torsion fields. So, there's no objective criteria. And the same thing, goes for special relativity. Oh, it's the simplest theory. That's not true. It's not simpler than the other geometries. In some instances, the mathematics will be simpler. In other instances, they will not. It all depends on what you're trying to use it for. And special relativity definitely relies on symmetry. Oh, it's this beautiful, beautiful symmetry we have. And symmetries it's its own whole can of worms, and at some point we'll need to do an entire video about symmetries alone because they are very, very misunderstood. But symmetries are something in modern physics which are made out to be very mystical, and they're made out to be the cause or the explanation of why reality is the way it is. But again, if you have a class of equivalent descriptions, yes, you'll have multiple mathematical constructs, and some of those constructs will have certain symmetries and not others, and some of the other constructs will have certain symmetries and not others, and some constructs might not have any symmetries at all. And the question is, well, why do you believe the symmetries are somehow more valuable or more inherent to reality itself? And the answer really just comes down to beauty. It's whatever the mathematician believes to be beautiful to themselves. And wherever you see mathematical Platonism advocated for, you see this justification of beauty. It's always there. For instance, in Wigner's paper, The Unreasonable Effectiveness of Mathematics in the Natural Sciences, he literally has a line where he says he gives his reason for believing all this, and the line he gives reads, "The observation which comes closest to an explanation for the mathematical concepts cropping up in physics which I know is Einstein's statement that the only physical theories which we are willing to accept are the beautiful ones." Now, as a note here, Einstein actually never ever said that. So Einstein was not a Platonist. Einstein was a positivist, and he attempted to only stick to correlations between observables. But as discussed in the last video, the inability to give explanation to anything, basically led to the Platonists coming in and invading and making his theories all about math and everything coming from math. So this quote here is misattributed. Einstein never said anything about only accepting beautiful mathematical theories. He may have said, and we were looking for quotes and couldn't quite find anything hard, but he said something along the line, that the laws of nature should be the simplest ones which account for all the observed facts or something like that. But it's a far cry from, what these mathematicians have basically appropriated, his ideas and his theories. All right, so our final thoughts here. Ultimately, we reject the idea of Platonism. To us, the idea, math describes things. Math is a language. And the laws of physics, don't tell you why the thing is happening. Instead, they tell you they precisely quantify, they preserve relations and precisely quantify them. So they'll tell you, if you see such and such objects or entities behaving in such and such manner, you can predict that such and such behaviors will result at such future times or other places. But again, the why is not accounted for in any of that, and for the why to be accounted for requires some sort of deeper modeling of reality, some sort of instantiation of physical substance, or perhaps psychological, conscious, spiritual substance, but something beyond just the math. For saying that math causes things, saying that math explains things is like saying that the language you're using to describe some phenomena is the cause of that phenomena itself. And now there are philosophies that everything is language. That is a philosophical thing. So maybe that'll be worth exploring down the line. Well, maybe we can rescue Platonism by asserting that all of reality is somehow language. And importantly, math is the language of our consciousness. It's how our mind makes sense of the world around us. So if we want to posit that all math is reality, that is going to probably lead us to some vein of solipsism, of consciousness as reality, which, is an idea to explore, but it would definitely one would seem to run into some sort of very difficult to deal with logical, recursive loops, though, if one posits that. And if the tools you're using to describe the thing you're describing is ultimately the same as the thing you're describing, well, gosh, that's going to get complicated and confusing fast. But, we try to keep an open mind, so we do reject Platonism for the most part. But hey, everyone can be wrong sometimes. So why don't you let us know your thoughts in the comments and let us know what you want to hear on these future discussions. And other than that, we hope you enjoyed this, and thank you very much for watching. Please like, subscribe, and do whatever you can else to help promote this. So we appreciate you all. Thank you.